Hi, I'm Jim Hatton, and I'm going to be talking to you today about developing a stream reach ranking system for the Southwestern Willow Flycatcher. My co-authors are Matthew Johnson and Jennifer Holmes, both of which have spent their careers out surveying for birds like the willow flycatcher. I work for the Columbia River Research Lab, the U.S. Geological Survey, and I have been involved with modeling flycatcher habitat for about 20 years now. So what we want to do here is to scale up from the original satellite model that I developed 20 years ago with Charles Pradzik and the Arizona Game and Fish Department. This is a 30-meter pixel model. It's very good. It's used all over the range of the flycatcher, and it's still considered to be very useful. But we also thought it would be useful if we could rank habitat at larger than the patch scale, which currently the satellite model uses the patch scale, about 120-meter radius. What we wanted to do is see if we could use the satellite model and extrapolate it over broad areas and then characterize characteristics of the riparian vegetation at that much larger scale, and then be able to rank the reaches so that managers could look at it and think about restoration and enhancement activities. So our methodology, we're going to run the satellite model over the entire Gila River Basin, and we're going to characterize habitat in areas that the Fish and Wildlife Service delineated as flycatcher critical habitat. And there's 7 large reaches in the Gila River Basin that are flycatcher critical habitat. And then we're going to compare it to the other reaches in the basin that are not flycatcher critical habitat. So we're going to use the flycatcher critical habitat reaches as training grounds for developing new habitat metrics that we will then apply in a rank model in order to see how many of those 7 original reaches we can correctly classify, as well as the remaining reaches in the basin. So as you know, the Gila River Basin is divided kind of right in two between Arizona and New Mexico, and it has quite a few flycatcher breeding grounds on it. So we thought that it would be a good location to try out this new reach rank model. And if it works well here, then we thought we could extrapolate it throughout the flycatcher range. So what we did is we divided all the reaches of the Gila into what we call zones. So we have the 7 critical flycatcher habitat reaches, which you could see are the red polygons. And we also delineated polygons for the other reaches. So there's a total of 60 reaches that we identified. Each one is a zone, meaning that a polygon's been drawn around the reach. And that enables us to use GIS zonal statistics in order to characterize the flycatcher habitat. It's an extremely efficient way to model large areas and large data sets. Quick overview of the original satellite model. It's 30-meter resolution. It was developed along the Gila and San Pedro and at Roosevelt Lake at the end of the 1990s. I helped develop that model as the lead modeler, and I worked with the flycatcher surveys for the non-game branch of Arizona Game and Fish to develop the model and test it. And what it does is it relies on satellite data. It uses the normalized difference vegetation index in order to identify the density and lushness of riparian vegetation in 30-meter cells. And then we segment that using different scripts to look at how much vegetation falls within 120-meter radius of any cell. And then we calculate this, we can literally calculate the size of the patches, and we can calculate the edges of the patches and the heterogeneity in that vegetation. The model's been tested quite a few times. The last big test was in 2016 when I extrapolated the model range-wide and actually looked at the density of flycatchers within the 5 model probability classes. And as you can see, it has an exponential relationship. So you're about 30 times as likely to find a flycatcher in a 5th probability class as you are in a 1st probability class. All right, so how did we do it? We ran the satellite model and created 4 new variables that characterize the habitat in 60 reach zones. The first variable was how much habitat greater than 40% probability that the satellite model calculates is in each reach zone. So it's actually calculating the percent of the reach that's covered in habitat. We also looked at the top 3 model probabilities, classes 3, 4, and 5, and we averaged those. So what we're doing there is we're trying to discern whether the highest probability classes, are a good delineator of habitat. We also looked at the average number of years that flycatcher habitat persisted between 2013 and 2020. So we ran the satellite model between 2013 and 2020, about the same date every summer, and then we averaged that, summed it up to see which cells had the highest values and which the least. And that corresponds to the number of years in which habitat persisted at any given area within that reach. And then lastly, we used the NHD plus GIS layer, which is the National Hydrography data set, to assign the largest annual flow to the reach. So NHD exists for the whole country. It's a beautiful data set. We are able to use zonal statistics to extract out that maximum annual flow and assign it to each reach. So this is what it looks like. On the left now, we have a map of model probabilities of greater than 40% averaged across reach zones in both the critical and the non-critical flycatcher habitat. So this is one of our 4 predictor variables. And then on the right, you can see we just use the zonal statistics to average those values across the zone. So the orange group is your critical flycatcher habitat, those 7 reaches that you can see delineated. They have, we compare the values that we found in those reaches compared to all the remaining reaches out there. And you can see there's a very large difference, much more area covered in predicted flycatcher habitat in the control group. The second model was the top 10 probability classes averaged across the reach. And once again, you can see that there was a clear delineation. Those 7 reaches, if you want to think of them as controls, they had a much greater, much higher model probabilities when averaged across those reaches than the remaining 53 reaches. And then the third plant variables, all derived from the normalized difference vegetation index, persistence. So what we did was measure persistence across those 60 reaches and within those 2 groups, critical flycatcher habitat and non-critical. And you can see that predicted habitat persisted for much longer periods in the control group than the non-control group. That's the first time that I'm aware of that type of analysis has been done. And then lastly, we looked at the average annual flow in each zone. And you can see that for the critical flycatcher reaches, there was much higher average annual flows than in the non-critical reaches. Okay, so now I'm going to show you how we rank the habitat. Those box plots that we looked at, we can derive the 25, 50, and 75th percentiles and use those as probability thresholds to create binary predictor maps, zeros or ones, for each of those 4 variables that we looked at. So we experimented, looked at the 25th probability percentile and the 50th percentile, and we decided the 25th percentile did a better job at delineating those 7 critical habitat reaches. So from here on out, I'm talking about the 25th percentile in that control group to create those binary habitat predictor grids. And here they are. You can see the 4 that are used now for the ranking scheme. Predicted habitat, 25th percentile on the left. The top 3 probability classes lower right. The flow magnitude on the lower left, and then habitat persistence on the upper right. So these are zeros and ones now. Anything above the 25th percentile of that control group we use to create that binary grid. And then we averaged them all together. We stacked them all together. So now you have cells with values from 0 to 4. If a cell had a value of 0, that meant that none of the cells in that reach contain one of those 4 predictor variables above the 25th percentile as compared to the control group. And if it had a value of 4, it means that all 4 variables said, yeah, you're above that 25th percentile. So that's the highest probability class. All right, so looking at this ranking system, the 60 reaches, you can see that there's 2 important breeding grounds that we just wanted to quickly check. One is the Gila Cliffs on the right, and the left is Fort Thomas on the left. They both have a lot of flycatcher breeding. And we just wanted to see if this ranking scheme did a good job of capturing those areas. And it did, so that gives us some confidence that this methodology is working. Of the 60 reaches that were ranked, 30 had 0 values, and we don't think they have much conservation potential for the flycatcher. Of those remaining, they just broke out that some were found in class 1. You can see some main stem habitat, which surprised us. Others, class 2 and class 3, are found in tributaries and a little bit in the main stem as well. And then the 4th highest rank is all were found in the main stem itself. So it appears that is sorting these areas out by hydrology and by the characteristics that we identified for the flycatchers. Okay, the methodology appears useful and repeatable. We really think that this is a methodology that has great potential to be extrapolated through the range, as well as refined regionally, because you can apply the model to any area, and then you can actually modify those thresholds for those 4 predictors. So if you have a control group, you can always apply the same methodology, look at those box plots, and look at which percentiles do the best job of identifying your control reaches. And then you can literally use that set of values to run the model in that a different area. Okay, so we think that the model appears to do a good job of pulling out the poor habitat reaches and areas with low persistence of habitat. And we want to emphasize so that's not necessarily bad for that predictor, because flycatchers like flooding, they like heterogeneity. So floods can really knock down the older trees, and you can get young willow and sprouting up, and within 4 or 5 years, those flycatchers are all over those areas. But it can also identify the areas that we think have been impacted by fires, insects, and droughts. So we feel good about that. The model can be used to determine what factors are limiting. So remember, we have 4 predictors, so we could do an analysis for any given area and identify whether it's limiting by hydrology or it's limited by the persistence in habitat And when you think about it, that's super handy for managers to know. We do think the model needs to have further testing and refinement in order for it to be as useful as it might be regionally. But I've already identified or said that it's so flexible that we think that we could extrapolate this to other areas and do quite well with it. We do think that additional development of the model at finer spatial scales could be used to guide restoration enhancement actions at the subreach, patch, site level. So here we use reaches that were kilometers long, many kilometers long. But there's no reason why you can't use this approach on 100-meter long reaches and use the same approach. And I think it would work well. So that's what I have for you. I hope you've enjoyed the presentation. I'm looking forward to answering any questions that you might have. Thank you.